Hey guys, this is Mrs. Harbin, and this is Pre-Cal. We are looking at Chapter 4, Lesson 5. Now, we have spent so much time this year with the trig values. We have looked at trig ratios, we've looked at the law of sines, we've looked at the law of cosines. We have spent who knows how much time we've spent memorizing that unit circle and practicing learning those values by memory. And we've graphed the sine function, and we've graphed the cosine function, and we've graphed the tangent function. And clearly we have not done all of that work for nothing, just to put it away and never see it again. So welcome back, trig functions. Today in this lesson, we are going to look at the inverse of trig functions. And in order to do that, it is really important that you remember the unit circle, that you remember your trig ratios, hello right triangles, and you remember what the graph of trig functions looks like. There was a reason that I kept putting that on that quiz and putting it on our warm-up and putting it on your homework, because you really need to know it. Our biblical integration for this unit continues to be that God made angles a part of our world. They represent a place where things come together, as well as how things are oriented to each other. Unlike lines, which are infinite, angles show God's use of a finite system of measurement. And the special type of angle that we're really concerned about in this particular lesson is the right angle. And we have seen that right triangles and Pythagorean theorem are useful in ways that maybe we never realized when we first learned about those things. They can really help us to analyze the distance of things, the movement of things. We can use triangles for a lot of different things that we probably never even realized. So we are going to be looking at some right angles today. Our lesson objective for today is that you, the student, will define, evaluate, and graph inverse trig functions. Define, evaluate, and graph inverse trig functions. So let's take a quick review, a quick stroll down memory lane, and hopefully you remember our three trig ratios. I'm just going to abbreviate them here. But when we are looking at a right triangle, let's say we're looking at this right triangle, well, sort of right triangle, sorry, right here. We're going to say it's a right triangle, and we are trying to solve this right triangle. This is our angle, our theta. We know that the sine of an angle is equal to ratio of the opposite side over the hypotenuse. And we know the cosine of an angle is equal to the adjacent side over the hypotenuse, and we know the tangent of an angle is the opposite over the adjacent. It's also our sine over our cosine. So we have that SOHCAHTOA, that made up little word there that math students have been using for years to help them remember those trig ratios. And trig ratios are helpful when we are trying to find missing information regarding an angle or the side of a triangle. Also, please remember that in the unit circle, the first coordinate when you're looking at your radians is the cosine value, and the second is the sine value, and that should have an E there since I wasn't abbreviating. So if you remember our unit circle here, let's say our 45-degree angle here, which was pi over 4 in radians. If you remember the values there, it was root 2 over 2 and root 2 over 2. That was our cosine of 45 degrees, and this is our sine of 45 degrees. So the unit circle is just a helpful trick, a helpful way to remember some of those common angles, like 30 degrees, 45 degrees, 60 degrees, which we can also write in radians. Remember that pi over 4 is just 45 degrees. So just a quick reminder about those things before we move on to inverse trig functions. All right, today we're going to be looking at the inverse of these trig functions. So let's find the inverse of y equals sine x. Here is our original sine function. You should look at this and know this by now. It is an odd function because it is reflective over the origin. Notice that it's hitting those points exactly. Some of you, when you are still drawing your sine functions, are getting like kind of here and here and here and doing all kinds of wonky things where you have the general shape, but you're not hitting those correct points. So here is our sine function, y equals sine x. Remember that when we're finding the inverse, we're just flip-flopping our x and y. So this would be x equals sine y. Well, sine is not a number, a coefficient. We can't just divide by sine and get y equals x over sine. In fact, it just requires a totally different symbol for the inverse. And this is a symbol you've seen on your calculators. We've actually used this symbol already. We've used this button already, even though you didn't maybe know exactly what you were doing. But this is where that sine to the -1 is used. That is our sine to the -1 or inverse, also called arcsine. And how we write that is this. Okay, the sine of -1x equals sine to the -1 sine y, or y equals sine to the -1 of x, or maybe your calculator doesn't have that sine to the -1. It has this button instead. These are the same thing. Inverse of sine or arcsine. Those are the same thing. So depending on what your calculator has, you may see one button or the other. Now, just because I'm referring to a calculator doesn't mean that we will be using a calculator to solve these. We can solve these without a calculator. Granted, some of them are easier than others to solve, but we can do all of them without a calculator because we can do hard things. So when we're talking about the inverse of sine, how we would read this is y is an angle whose sine is x. Y is an angle whose sine is x. So we might be given the sine, and then we have to determine what angle we're talking about. So if I said y is an angle whose sine is √2/2, you would say, oh yeah, that's that pi over 4 or 45 degrees. Y is an angle whose sine is x. And so let's take a look at some of these in just a moment. First, let's look at the graphs here. The inverse relation of y equals sine x is not a function. Our original sine function is not 1-to-1. And so based on that property of 1-to-1 functions, we know the inverse is not a function. If we pass a horizontal line through here, you can see it's passing multiple points. All periodic functions would fail that horizontal line test. If we look at our inverse graph right here, you can see it does not pass the vertical line test. So it is not a function. If you're wondering how we got this inverse, remember that we're just reflecting over the y equals x line. So take, for example, on the original sine function, our point was pi 1, and on our inverse, it's 1. I'm sorry, that's not pi 1, that's pi 0. And so here you can see 0 pi on our inverse. Mark that point right up there. We can also pick up that whole thing and flip it over the identity function, which we may do in class so you guys can actually physically see that being reflected over that line. Either way, because this is not 1-to-1, the inverse is not a function. The domain of y equals sine x then must be restricted so that we can have a 1-to-1 function, so that when we're looking at the inverse, we're still looking at a function. And so the interval that we're going to use to restrict our domain of the original sine function is -pi/2 to pi/2. Capital letters are going to indicate this restriction. So capital S sine x and capital S in the inverse tells us we're dealing with a restricted domain. Let's go back and look at our graph here of the -pi/2, pi2 interval there. So -pi2 is right here, and we're restricting it to pi2. So when we're dealing with sine and the inverse of trig functions, we're dealing with this restricted domain, then that is what that is going to look like. We're dealing with just that restricted part. Our inverse restricted part then would just be from here to here. This piece right there. So we're restricting that domain so that it is a function, and this is the interval that's used. -pi/2 over pi/2, and it's notated by using a capital S. This indicates that our domain has been restricted. Oh, there are the two graphs right there. I didn't need to go back and draw them. All right, so let's put the graphs aside for a minute and rely on our knowledge of unit circles here. We were given this problem, y equals the inverse sine of 1, or arcsine of 1, and we want to find y. Remember, we can read this as y is the angle whose sine, this whole part, can be read as the angle whose sine is. That's what that arc sine means. Y equals the angle whose sine is 1. So this is going to require some knowledge of either the sine graph or the unit circle. So think through the unit circle, go through those sine values. What angles do we have between negative pi over 2 and pi over 2 whose sine is 1? What angle from the interval negative pi over 2 and pi over 2 has the value of 1 as its sine? And that is pi over 2. 90 degrees, if you're trying to think of that in degrees instead of radian. 90 degrees is the only one that has the value of 1 as its sine. So y equals pi over 2. Again, the unit circle would have been really helpful there, knowing that unit circle, but we could have also looked at the graph and said, on our arc sine graph, 1 and, where is it 1? It's 1 at pi over 2. And we could have looked right there at that graph. So knowing both the graphs and the unit circle can be helpful for solving this information. The cosine function is also a periodic function. It's not one-to-one, so we also have to restrict the domain on it as well. And so when we restrict the domain of the cosine function, we restrict it to 0 and pi as the interval. Tangent is also periodic, and the tangent function also has to be restricted, and it's restricted to negative pi over 2 and pi over 2. And that's almost identical, or that is identical to the sine function. Let's go back and look here. We've got negative pi over 2 and pi over 2, and our cosine function is 0 pi, and then this is negative pi over 2 and pi over 2, but please notice, though, that in this function we've got parentheses, which means those endpoints, that negative pi over 2 and pi over 2, are not included. So pay attention to the interval for tangent. Right. What about when we're trying to find the inverted or inverse cosine function for a value that is not on the unit circle? Well, this is where the Pythagorean theorem can come in play. When we look at this, we're trying to find two different things. We need to start with the innermost piece and work our way out. So the first thing we're trying to find is the angle whose cosine is. Remember that this whole inverse trig functions can be read as whose film the trig function is. So whose cosine is 3/4. Unfortunately, we don't have that on our unit circle, so we're going to have to do some work. After we've found the angle whose cosine is 3/4, we then can move to the outer piece and find the sine of that same angle. In order to help us with this one, let's refer back to the Pythagorean theorem. We have an angle whose cosine is 3/4. Remember, cosine is adjacent over hypotenuse, so we're going to draw a triangle here. We're going to put our angle, because we don't know it, and we're going to label the adjacent side as 3 and the hypotenuse as 4. We're then going to use the Pythagorean theorem to find that missing side. So 3 squared plus x squared equals 4 squared, and when we solve for x, we get square root of 7. Okay, now that we know this is the square root of 7, we can now find the sine for the exact same angle. We don't actually need to know the specific angle here. Sine, if you remember, is opposite over hypotenuse. So the sine of this angle is root 7 over 4. Okay, and we have now solved for y. We didn't actually need to know the specific angle value there to decimal point or anything like that. We just needed to know the sine of the angle whose cosine is 3/4. So we had to kind of work our way inside out. Let's try another one. Find cosine -1, so the inverse cosine of negative root 2 over 2. Well, knowing what we know about the unit circle, we know negative root 2 over 2 is over here in the second quadrant. Over here, we know exactly where it is. And the reference angle, that's this angle right here, is pi over 4. That's the reference angle. It's not the exact angle. It's not this measurement. If we know the unit circle, we can just pick out exactly what that is. If we're not sure what the unit circle says that number is, we may have to go back and